My name is Nagraj Medi. This question is for Gabriel. In your designs, do you guys actually build not the CFD thermal model, the real PC board model, thermal model with thermal chip? It's important. And
you mean in the simulation or? Not
simulation. Do you actually plan on building?
This device that I showed was completely built, from start to end.
No. Thermal board. Do you build a thermal board
okay, yes,
before the actual PCB is made?
We do that, yes.
We do that?
Yeah, and we call it TTV.
There's a couple different ways of doing it. There's the TTV, thermal test vehicle.
Yeah.
Our TTVs that we are used to tend to only power the main processor. However, as in the typical evolution of a product, depending on what company, you might call it EVT, DVT, PVT, or phase 1, phase 2. Gabriel's always sure, I happen to know, to make sure that it's tested as early as possible, not just to look for thermal difficulties caused by mechanical, but powers. Would this be shocking to someone that powers are sometimes higher than our electrical friends have told us? Things like that, So he may.
I did it from Sun Microsystems and on the workstations. Very first TTV built on the workstation.
So really that's what I meant before the tooling phase. We try to do something to simulate it experimentally, so it's not the real thing, but it gives you some kind of power profile very close to what you're looking for.
Thank you.
So that's what we do.
Okay, please come on up, Jesse.
Hello, Jesse Galloway from Amcor Technology. I'm holding up my Apple phone. And if you notice on the back, because I'm so clumsy, I have to put it in a case. And you'll see this on tablets. People want to protect it, and they just kill your thermal solution. So I have two questions. Do you account for the protection they put on to degrade the performance? And have you ever thought about the protection they put on could actually enhance the thermal performance by extracting more heat? And that's open to anyone who wants to answer it.
Anyone? Andrew, just adjusted your glasses. You're up.
A couple of things to note. If the device is very large and you've spread the heat evenly across the device, you can put a case on it and it doesn't change the resistance too much. And the internal temperatures may go up a little, but there's kind of a knee in that curve, so you can calculate that. And if you can't increase the overall surface area, then it may be difficult unless there's, so a product that's not already spread the heat well, then you could have a heat spreader in the case. But the device you held up is, that they do a pretty nice job of spreading the heat. You could adjust the software to know that there was a case, and then you could make sure that you weren't unnecessarily throttling. And we don't do that yet. But that's for me.
Guy, please.
Yeah, if you take a look at the way a case is built, you've got a fairly large surface area, but they're usually fairly thin across the back. And in doing that, they really don't add that much thermal resistance because of the large surface area, the ratio of the large surface area to the actual thickness of the case. So it doesn't hurt you that much.
Emil, do you assume that people are going to put a case on their pixels?
Yes, and from, again, strictly ergonomic point of view, what I've noticed is you gain a little bit on the back surface because the back of the cover is not as hot as the phone case, but you end up increasing the display temperature. So the display ends up getting hotter than, because the whole phone basically goes up. The biggest problem I've seen in looking at different cases are the solid cases that don't necessarily conform too well to the back surface and creating any kind of air gap. These are the worst. And maybe mechanically they're okay, but that's a problem. There are some cases in the market right now with NFC tag or NFC sensor, and we can definitely, I think that's a great idea that, you can adjust your thermal management in a way that the phone would recognize, or the software would sense that there is a back cover, and then you won't have to throttle at certain temperatures. So you kind of change the calibration between your PCB sensor and what you predict the skin temperature to be.
Jie, please continue, because you spoke most about thermal management, the temperature control. So with and without the case, what happens? Is there any way to plan around it? What's the improved situation?
My answer is yes, and there are some different strategies about it, and that's all I can tell.
Okay.
Sorry.
Okay. And Gabriel, I want you in here too, because I believe one of the reasons people put covers or cases on their devices is for protection, for drops, et cetera. Now, I realize that when systems are originally designed, they're designed to achieve some level of durability for given drops. But cases tend to increase that. How do we decide what's the amount of protection someone needs to maybe at least get out of them putting the case on for extra protection?
So I know of one company that's flat out says, I protect, and brings data. It's OtterBox, I think, and they claim that. But the others, they cannot claim it. I believe that it's a perception thing, and it's more for surface scratches, that I keep my phone clean, scratch-free. I don't believe it makes a huge difference in protecting it. Maybe catching the glass edge in certain cases, but that's about it. It's a crack initiation problem more than really robustness.
Okay. All right, so until we get device manufacturers to carry dozens of colors and designs and textures, it looks like maybe we're doomed to have covers in our future. Thank you. Okay, anyone else? Thank you.
Hi, my name is Josh Goldberg. I actually have two questions for you guys. The first one is with the phones and tablets and laptops becoming more power dense, faster, that type of thing, what do you see as maybe a more predominant cooling technology used in those devices as we progress? And then the second question is with wearables specifically. You'd mentioned things like watches and the VR goggles and things like that, but there's a lot more wearables coming out there, like full-on body suits and things along those lines. So what sort of cooling do you see as being feasible for those types of wearable devices?
Okay, those were two large ones. Repeat your first one, because I'm going to have us go back and do that one first.
Sure. Yeah, the first one was what sort of trends do you see for cooling technologies and things like smartphones and tablets and laptops as the powers progress more and more and we get faster portable devices?
Okay. Anyone?
Okay.
Guy?
You have to realize that it's the surface area of the device that controls how much heat you can get out of it under natural convection conditions. And if you can't increase the surface area anymore, and your emissivity is already at a maximum, usually around 0.8, 0.85 for most surface finishes, then the only thing you can do after that, other than breaking the laws of physics, which no one's figured out how to do, is to put some kind of an air mover into the system.
Now, Andy succeeds in putting in air movers and still having it thin and elegant.
The air mover was, when we did Pro 1 and 2, and that was a very thick device, and it had two blowers in it. And when that was my first mobile device, and I thought this is way too thin for blowers. When I look back on it, it seemed quite spacious. Those blowers were still reasonably good. But we've worked pretty hard with our suppliers on making thin blowers as good as they can get. It seems maybe there's some inherent limitation there. And you could see, we'll put that back up quickly. Is this all right to do this? You can see our thermal modules and how they're growing. And so taking traditional technology like heat pipes and kind of thinking of them in new ways. Like Guy said, it's surface area, so it's how you communicate the heat. Like Gabriel said, the SOC, the very high density heat, needs to be transformed to the surface area of the device. And so it's kind of it's like everyone leaves the city and goes home, and there's congestion. And so how we can apply high thermal conductivity or equivalent, the heat pipe has fluid in it, so whatever enables a very low thermal resistance path, and as you get further away from the city and you're exposing more and more surface area, you can go to lower performing materials. So it's kind of like a river delta or something, or a vascular system.
Anyone else? Emil?
So again, as the guys mentioned, that with the current form factor, all we can do is just to spread the heat as evenly as possible. Once we reach an isothermal point where the whole device is at the same temperature and it's the maximum temperature we want it to be at, anything beyond that we'll have to use what we're expecting to see and start to see a little bit is a lot of the computing happening on the cloud, and the device itself is only having the Wi-Fi or the connectivity like an RF package active, while not doing all the computing in the device itself, because again we're constrained by the surface area.
I'm asking you to hold on for a second, because I want to continue this thread for a moment. I know that when I was working on thermal management for an early tablet at a company, we're talking about you need to handle more power or it's going to get too hot. And they were told, oh, don't worry, the software will come in and reduce the temperature for you. And management said, oh, okay, that's fine. And then in the end, when we tuned it to do so, and they found out it reduced performance, they lost their minds. But so that's the other thing that's not there is, you can just allow a higher touch temperature. But other than that, we're brushing against the laws of physics. Okay. Yeah. So your second question, please go ahead and repeat it so it's fresh in everyone's mind.
And the second question was, you'd spoken a little bit about wearables like the VR goggles and the watches and things like that. But with a lot of other wearable, especially in the medical field, devices coming out that are more like body suits and things along those lines, how do you guys envision thermal management to be in cases of those types of electronics that are coming out?
I'm going to ask Guy to start for this one.
Okay.
Oh, I'm sorry, please.
I'm sorry.
A little louder.
Couldn't hear it. Sorry. I'm not very good at karaoke either. So my question was that with other wearable electronics like body suits and things along those lines, how do they envision thermal management for those types of electronics, not just the ones that are the watches or the VR goggles or things like that?
Yeah. For instance, I'm working on a project right now. It's a medical device that's to be worn against the skin. And the first thing we did was we took and did a study of the thermal conductivity of the skin. The body has a core temperature of around 37 degrees Celsius, plus or minus a couple tenths for a healthy person. When we did this thermal study, we were actually able to build a model of the flesh over the core temperature. And then after that, we take and we do a CFD analysis of the unit that's being worn against the skin. And as was mentioned, while the touch temperatures for the hands and everything are somewhat higher, if you have something in permanent contact with the skin for several hours, you can actually cause damage at around 43 degrees Celsius. So we tend to design the unit so that it doesn't get much above 40 to 41 Celsius. And the only way to do that is to keep hot components away from the skin side and make sure that most of that heat leaves through the part that is away from the skin and radiated and convected out into the air.
How well does that work then if they're wearing like clothing or a jacket?
Well, that can be a real problem. When I model it, I do model it with, say, a shirt on, but if they actually have a coat on, that can be a real problem because there's no good way to get rid of that heat except make sure that the device isn't dissipating so much power that it is raising the skin temperature above the actual limit that's allowed for continuous contact. And at that point, about the only thing you can do is start throttling the device with temperature sensors in it to keep things cool enough.
And I'd like to reinforce Guy's position on that. If you look at the IEC international standards for temperatures that are allowed to come into contact with skin, once it's allowed to be in steady state contact, it's basically skin temperature that they're allowing, almost no temperature rise at all. So if you're relying on this device for a health monitor or a sports monitor, well, I'm not sure we have any other ideas yet. Anyone else? How do we deal with these passive devices specifically, or ones that are passive now, as we want more computing, want them touching the skin under our clothing? Anyone? Andy?
Maybe just to comment on the challenge there. The most sophisticated device I know of is myself, my body. And as an engineer, I think for a long time I didn't want to admit that. And even topics like biomechanics, the body is so amazing and you're threatened by it as an engineer. It's the level of complexity and all the things it does. And so when you start putting things on it, it's just not a trivial problem at all. And the amount of work to go figure out when skin is damaged and all the different people and age groups and you end up not being able to hardly tolerate anything when you're doing a product that spans every person. The point is that it's really challenging. It takes it up quite a bit.
Okay. Emil, Jay, any other comments to add?
Just one quick comment, and again, it's to reemphasize how big this challenge is. We need maybe to develop something to decouple the heat source from the body as much as possible. And we never thought, in thermal management much about insulation. We're always trying to spread the heat and trying to, isothermalize something. But when it comes to permanent or constant contact with the skin, this is something worth looking at, how we can actually insulate and protect the skin and direct the heat away in a different direction.
Oh, there we go. If I'm not mistaken, the translating Google earbuds actually rely on computational power on the user's belt.
Okay. Absolutely.
Okay.
I think as long as you don't put that on your head, then it's challenging, but we will find a way to manage the heat. But if it is on head, then it's very challenging.
Gabriel, are people going to go for consumer devices where you have to have two different parts? One's the convenient one, and one is kind of the computer that's got to be on your belt or, in your purse or something?
The example was given about the cloud, right? This is, Emil, I guess, talked about that. I believe that us in this room, we're here to stretch the envelope. You can stretch it so far. And after that, you have to go back to the fundamentals. That means you have to look at a semiconductor that can do more with less power. Have to bring the power back.
Okay.
I give you an example. I think that I was challenged to put a tablet together in 2007 that was around 420 grams or something like that. It was an 11-inch. And I kept using all kind of exotic materials, going back and forth and everything. And at the end of the day, I said, I went back, it's like, I'm at 460. I can't go any lower. But I have a suggestion for you. If you take 1/3 of the battery off, I can go down to 400. no problem. And guess what? This is exactly what we did. Because we worked with the LCD supplier, we worked with different, the ones that take the most hog the power, and we were able to do that.
So taking a systems and evolutionary
Look
approach.
at it in a system kind of, ingenuity type. I think Andy alluded to that as well. It's doing things, stretch them all the way to the end, and then when you can't, stretch other places. But you have to use your multidisciplinary friends. There is no other way about it.
Okay. All right, thank you. Okay, next. Come on up so we can hear you, please. Thank you.
Because of all the touch temperature that we are talking about, especially in the mobile phones and tablets, Intel is thinking about designing instead of maybe reverse engineering, like SOC. There is no system on chip, okay? Yeah, you separate the power module and the eCache module and the main the frequency module, okay? Yeah, separate them, and so they'll all be dissipating smaller heat, but we know that performance will be affected, okay?
But in different places. And I think that
if you have room,
I think Intel did this in smaller scales than what you are describing.
Yeah.
In the last generation of Skylake, I believe, right?
Yeah.
And this is what I was alluding to actually in what I was talking about, that you have to talk to the electrical engineers.
Correct.
Because you can sit with them, and if you have only one point load, that's everything in it, the SoC, you can at least get them to put it where you want it. So you can pipe the heat the best way you can. You can talk to the semiconductor guys and say, well, what can you chip off of here? I need it somewhere else because, taking all the people to the city, like Andy was saying, the buses will not be enough. I need some other place, right? Some other distribution center.
Yeah.
So, and I think this is a longer term.
Longer term, even the CPU,
Yeah.
Okay. Yeah, on a server or a motherboard, it was fine, Okay, we may have to, coming from Sun Micros, I also worked at Intel and Folsom, mobile processor.
Right.
Yeah. Mm-hmm. I think we may have to do all that, power sources. Yeah, let it not be any more than 100 milliwatts, each any component. Yeah, if you have room, like tablet and mobile phone. Thank you.
Okay, thanks.
I believe actually that it was the voltage regulators that they separated in certain instances to do that, what you just said.
Hi, my name is Hidden. So I have a question about the heat transfer for passive cooling devices. So what is the percentage that heat was dissipated by radiation for the outer case? And what about the from the inside the component or PCB into the case? Do you consider the case material to have like a high emissivity to enhance the radiation? And that's my question.
I let Mark answer.
Okay, well, so Guy.
Okay, I've done quite a bit of work in that area.
You mentioned that.
If you took a look at the slides I was putting up, over half of the heat is leaving due to radiation. It's more than the convective part. And in order to get that maximum heat out of there, you have to do a really good job of spreading the heat so that all the surfaces are running at a fairly even temperature. In other words, all the surfaces are participating in removing the heat from the system instead of just some hot spots. Okay, so that minimizes the overall temperature of the system, and it minimizes the hotspot temperature. Now, did you have a second part to the question?
No, just the slides you show, was that for a tablet?
It was for different size. I showed a couple tablet sizes, and I went all the way down to a phone size that was limited to around 3.5 to 4 watts.
Was that for like the outer case heat dissipation?
That's the outer dissipation. But you have to remember, any heat you generate inside all has to leave through the case. It can't escape any other way. So
Understood.
all you have to do is worry about removing that heat from the case. Once you have spread out the heat properly inside.
Were you asking about radiation internally?
Yeah, as well.
Because sometimes you open devices and see that they're painted black inside.
Yeah, actually, I do have a question. Sometimes if you open the Ultrabook or something like, you see the black cover. So I'm wondering what kind of material is that? Is for EMI or thermal purpose?
Inside the radiation, the surfaces aren't exposed to the ambient, so there's not a big temperature gradient. And mostly, from what I've heard, and from measurements we've taken as well, that those are, the inside of the devices are made black so they will look good. Or perhaps maybe if you have vents, then you can't see inside. But it doesn't usually help much.
That's what we call under the hood aesthetics.
Yeah, it is.
I was going to say, we've actually done some CFD simulations where we changed the emissivity of the components inside, and it didn't make a lot of difference.
No.
Probably because the area is small, right?
Yeah, you're working in such tight spaces that the most of the heat inside is conducted through the thin layers of air.
Yeah, it's not until you get to the outer surface that your other view is at ambient. Otherwise, all the temperatures inside are fairly close, so.
Okay. And while the next person's coming up, I'll mention Wien's law that if it's black, it's because of aesthetics. So while black receives sunlight at a higher heat flux than white, at room temperature and slightly above kind of things, it's IR, everything is a lower wavelength, and all polymers have about the same emissivity. It makes very little difference if it's clear or black. Yeah, the reason Apple makes everything black inside is so it looks beautiful.
So you can paint the outside white or paint it black, and the emissivity is basically the same.
Basically the same.
Yeah.
Now, if there's one tip, if it's aluminum though, anodize it.
Oh yeah, yeah.
Free
Do not
big-
have any shiny polished metal surfaces.
Yeah, free boost in emissivity from anodization. You heard it here first, folks. Bruce?
So Bruce Kennedy, formerly of Oracle, now Rogue. So I'm wondering, in terms of the dynamics of transients, to what extent are kind of performance metering to keep the, subject to maintaining a certain temperature within the device? And in that same vein, to what extent are people considering using phase-changing materials? Here again, just emphasizing the need for a constant temperature and dealing with dynamic loads. Any comments from anyone?
Andy, you and I have both looked at that. So.
Phase change materials.
Yeah,
And I don't think I noted it, but as you extend your thermal module and you engage surface area, you're also engaging the capacitance of all of that material.
Right.
And we see a great benefit in our ability to turbo. So the Pro 4 could run 25 watts on the processor for well over 200 seconds.
Wow, okay.
And then we settle down. And I think maybe we'll have to work at changing perception, because I think some consumers think that the device is throttling when it's actually coming away from turbo, which is a gift.
Yeah.
Turbo is a gift.
Right.
So that's unfortunate. But
right.
But then you're right. Once you could also apply like a wax that would melt. Is
Right.
that and then you could get an additional kind of a stall where the temperature goes up to the phase change of the wax, and then you
Yes.
you melt the wax.
Right.
And we look at that your company has done.
The thing is that these units are so tight inside for space that there isn't room for phase change material anymore.
Right.
And to add phase change material so that you can run longer in turbo mode means that the unit actually gets thicker. And
Yeah.
the ID people will not let you do
Right,
that.
to trade space.
Thicker and heavier.
Heavier.
too.
And
That's right,
heavier, yeah.
Yeah, okay. And then the other half of my question, let me just repeat it, has to do with performance throttling, subject to all these different conditions of the ambient temperature. Sometimes you can run more power, get better performance. Otherwise, do the machines or do the electronics just limit the performance subject to sense temperatures in the device? Is that common?
Definitely.
Okay.
We know, we spend a lot of time finding ways to know the temperature of the outside,
Right.
or independent of where it is or what it's doing, so that we can throttle.
Right.
And then throttle really smoothly so that it's
Yeah.
as good as pleasant of an experience as possible.
Right. Yeah, for the record, we did that with Spark Big Iron. Everyone has to do it at some point. Okay, thank you very much.
Reggie?
Thanks for the great presentation. The Moore's Law, a lot of people here from Intel, technology nodes are now moving more like 3 to 4 years versus 18 and 24 months. Technology nodes are now lagging maybe 3 to 4 years versus 18 to 24 months. And so people like Bruno Michel said this morning that you want to leverage 2.5D and 3D packaging to gain performance, interconnect delay, power, and so on. But from the discussion here, I know we talk about low power stuff, 17 watts. There doesn't seem to be any discussion whatsoever on 3D packaging. Is that something strictly from performance point of view, right? Is there going to be some thought process? I know in devices like iPhones and stuff, you have SoCs and you have some stacking, but I'm talking about stacking memories and logic and so on. So if you can talk about what the plans are for that, I'll appreciate it.
Thank you. Anyone?
Many phones have POP packages, so the memory is on top of the processor.
Well, that's the first. I think that's the first level. But now he's asking, are we going to go further? Are we going to stack memory die a number deep? Oops, no. Everything.
Yeah.
Just get 3D.
So I think from his point of view, miniaturization is a great advantage doing that. But thermal stuff is very complex. Then you're trapping the heat in between the layers. And modeling that stuff is extremely difficult, I guess.
There's no solution even at the high end, right? So I'm just curious. Is there any thought process at all?
I think it may be more of a high-end question than on the portable devices, because if you take a look at the processor, the junction temperatures on the portable devices, they're generally running well below the limits specified by the IC manufacturers. And it's almost always the skin temperature that is the limiting factor on the device.
Emil?
Yeah, this is a real problem, and you can see in the latest generation action camera, in order to handle the 60 frame per second processing, they went to POP config basically, and on top of meeting the skin limitation because of all the power, there was a problem also at the junction level because your junction to case resistance is dramatically higher when you have a POP versus two discrete packages. So, I mean, all I can say is you have to use thermal vias, you have to increase the content of copper inside the PCB, take advantage of the PCB, and it gets a lot more complicated when your whole device is only weighing like 120 grams and it's only 2 inches by 2 inches. But absolutely, it's a huge challenge, and I think it's going to get worse, especially with anything that uses AI image processing. at a higher frame per second.
Thank you. As our next questioner comes up, I'll just mention, I know, please take that I've seen Intel go back and forth, we would call memory down versus pop, and they seem to alternate every generation. They find the advantages someplace else and ping pong back and forth. Let's see where we settle.
Actually, the two last questions were also the same way. He's asking about how you make it denser, and he was asking how you spread it so you can take your power apart from it. So there is always that problem, you know, it's always the dilemma on how you're going to do your device. It's more of a system thing. But if the power gets too high and you layer it, it's very hard to get it out, to get the heat out.
For a small device, that's okay, because you can drive it into the PCB and spread it.
Mm-hmm.
And so it balances. You get junction and skin kind of hitting their limit together.
Mm-hmm.
But then if you have more place to reject the heat, a larger device, then you don't want to incur that resistance right over your major heat source.
Thanks for the great presentation to all the panelists. I'm Sridhar Sundaram from Samsung Research in Austin. It's a follow-up on Bruce's question. A lot of the mobile workloads, especially in smartphones, tend to be of a bursty nature, meaning for a very short time but very high power, right? Jie, you also pointed out that such bursty workloads tend to be junction temperature limited and not skin temperature limited. Some common examples are, very fast web page loading that all users demand, or very fast high definition camera shoot, or a very fast gallery view scroll on your smartphone. These are very high power but last maybe a second or less, right? So for such applications, seems like phase change material for energy storage to cap the junction temperature for a second or couple seconds would enhance the user experience. But I would like the panelists to comment on what's the trade-off between use of phase change material for bursty workloads like that versus potential increase in the overall steady-state thermal resistance, because you want both, right? There are long duration applications like gaming that can last 10 or 20 minutes, or if you're a teenager, maybe all day, right? Or as long as the battery lasts. So what is the trade-off there? And I'm not aware of phase change materials being widely used in mobile applications, at least not on Samsung phones yet. So can you guys comment on that? What's preventing it? Are there devices, solutions out there that have a good trade-off between energy storage capacity versus thermal resistance, low thermal resistance?
Allow me to start, if we may. So you used the exact word, trade-offs. So my personal rule for this was, if you're going to add a phase change material, it shouldn't decrease what we commonly term the steady state power budget. Whatever you can do steady state, don't put that phase change material in the way. I still want the regular heat transfer path so my steady state performance doesn't go down. And then the next requirement is, if this is going to do any good, it's got to be thermally very close. Physically very close. And that ends up being very touchy real estate. And so there's hardly any real estate to begin with. And now, if you don't want to get in the way of, the primary heat transfer path, there are people, in fact, I've talked to here, are working, trying to work phase change materials in. It's an interesting challenge. Who wants to? Guy?
In general, it's a space limitation within these machines. If you take a look at how the space is used within these machines, usually 2/3 of the space is battery. And in order to get the runtime to the point where it's an acceptable runtime for the user, you've got to devote that much to battery. And then the rest is the electronics and cooling and other internal peripheral devices. But in general, you're so limited on the amount of space inside that you can't put a reasonable amount of phase change material in there.
On that note, you have to communicate the heat to the phase change material, and it usually like a hydrocarbon wax or something, so its thermal conductivity is quite poor. And what we found, interestingly, is that there's a lot of thermal capacitance in the device itself. And so if you can transform the heat, you get that thermal capacitance. And this, if you look closely at this slide, the blue is the processor power, 25 watts in the Pro 4 tablet. And this is the total system power. This green is the junction temperature. So it's allowed to go to 90. So we throw 25 watts on the Pro 4 processor for 200 seconds, and the processor is completely able to handle that because it's hitting this is the thermal module. So it's instantly transformed from the 9 by 18 millimeter die to this huge surface area, and then it goes out in Z. And so if we were to add phase change, the calculation came out that we'd have to add like tens of grams of it before it changed it much over the capacitance we already are tapping into here. So we've found that the device itself represents a good capacitor, and that just transforming the heat is quite nice for the bursty stuff. We could handle more than 25 watts for shorter durations. And again, you can see here how the skin temperature, this kind of yellow line, is what limits us. The junction temperature is headed towards its limit, but the skin hits it first, and here's where we drop down.
I agree with everything you said, Andy. Just a quick follow-up is on smartphones, of course, the scales are much smaller, right?
Mm-hmm.
For example, when you do want to boot up the smartphone really fast, or you want to load a web page within a second, you may reach peak powers of single-digit watts, right? But you very quickly get to a junction temperature of the limit, 90, 95, within a second, because your die thickness, don't forget, is only 100 microns or something.
And the
right?
smartphones are pops. So
that too, that adds to the problem, right?
That's one thing I've run around saying, like, get that memory off there so we can put something thermally capable close to the die.
Right.
But it's the
so at
thermal
those
engineering.
short time scales, you don't get to take advantage of the capacitance in your overall system,
Right.
because your heat gets to travel only very short distances at such short time scales, and your silicon thickness is really tiny to keep the total smartphone your Z direction limited, right? So it's a big challenge, especially with the POP construction, like you pointed out, Guy.
Mm-hmm.
There is no room to add a phase change material, right? And all the capacitance in the rest of the skin and the PCB and so forth, such short time scales don't take advantage of that. So it is a real challenge for us. For very short bursty workloads in smartphones, it's a big problem. Thank you for the comments.
Andy also, he quantified that it takes tens of grams of this phase change material to make the difference. I can give you an idea of the volumetric. That device that I showed the exploded view of, we tried that. And the most we could stuff in, I mean, literally stuff in, with the existing enclosure was 6 grams. And then we went ahead and then made a rear housing that's different, just to put more in there. And that thing became very ugly very quickly. And not only this, it became heavy. So there was no way. But we did try that very hard.
To follow up on a couple anecdotes, in case you're not used to looking at the design of what's inside typical smartphones, et cetera, when I was doing designs for that, I actually had to switch from FlowTherm to something like Six Sigma ET so I could get the true form of the parts, include screws, et cetera, because it was so tight and so dense just to get an accurate thermal model. And yeah, I happen to know that a thermal engineer went to Gabriel when he was designing that device and said, if I can have 50 microns thicker, I can. You would think the guy attacked him with a knife. He's like, you want 50 microns thickness? Leave the campus and come back tomorrow.
Yeah.
There's no way you can swing this with any marketing team or ID team. There's no way. We all know that.
David?
Batteries?
What about it?
What, make the phase change in the battery?
Progress? Other technologies? Are we making progress on other technologies for
Battery.
batteries? that
Energy
reduce-
density you're talking about.
Reduce the volume consumed by the battery within the mobile device. It's a huge issue for vehicles, implanted
Yeah.
devices.
I think a lot of manufacturers are putting a lot of effort into that. I cannot talk about it.
Guy, you're more
No,
liberal.
I don't, I'm not privy to any battery technology.
Okay,
that
another
will do
simple
that.
question then.
Oh.
The vapor chamber, Gabriel, that you showed, was that titanium? Was it?
No copper, 0.55.
Okay, so not a flexible, not a PCB vapor chamber.
No. It was a regular copper vapor chamber, and the special thing about it was that the grid inside was customized for the temperature profile that we have in that product. So it was extremely efficient.
And if I heard you correctly, that never went to any production format.
No, this was purely for demonstration. And that device has a lot more to it than what I showed.
Well, please, we're listening.
Well,
I can't really talk about
yeah,
it.
it's a very, well, there have been, please come up to the microphone. As we all know, there are a few manufacturers who are now producing ultra-thin vapor chambers. Novark, who's here at the conference. We've also worked with people like AVC, and there are a few others who are mass production capable. And these vapor chambers work. At 0.4, I haven't seen very high power capabilities. At 0.55, these things are very impressive. If you need to spread heat and can spend a few dollars, don't hold back, you should investigate.
When we did this vapor chamber, I went to AVC myself, and they produced about, we brought into our factory at Intel, the prototype factory, about 400 vapor chambers, and there was no one reject, because we worked with them closely in the optimization of it, and even in their prototype line, they tested every one of them, and they had very, very little yield losses. They were very good.
My name is Pratish Parida from IBM. My question is regarding the modeling. Are the modeling tools at par that you needed to be designed, and also the measurement techniques? Are they also at par to be actually be optimizing everything from chip all the way to the package and systems? Or is there any development required? So for example, the vapor chamber optimization, is it empirically based or is it model based?
Can you answer?
I can start. The original vapor chamber work proceeded from totally empirical based, but now we're trying to bring it into model vapor chambers and heat pipes, both steady state and transiently as the next steps. As the vapor chambers become more capable and more repeatable, it's worth developing models for
But
them.
I think your question was more about manufacturing the vapor chamber empirically, like expected performance, or more like modeling it once you put it in a device.
Everything.
Right?
Let's say
Everything.
Everything. Let's say
I think
even
he
on-
was geared more towards, can the manufacturer, if you tell them I want a vapor chamber that does this, this, and that, can they model it or they do it empirically, right? Am I understanding you correctly?
Yeah, so vapor chamber is just an example, but also, for example, the guy from Huawei, even to do optimization, you need to run thousands of cases, right? And you need some kind of resistance model or reduced order models, right? So are the CFD good enough, or you want reduced order models which are also good enough? And what is the trend that you need to actually be optimizing? That includes the vapor chambers as well, because that's also a very complex problem, right?
Since you mentioned reduced order modeling, Jay?
Yeah, so the future customers will have more application case scenarios. Now, the newly released smartphone has like a dot projectors and other AR applications. So I think there will be thousands of new applications and case scenarios. So probably traditional CFD tools is not good enough. We need more.
And as far as the design of heat pipes, vapor chambers, et cetera, I'm a believer of when I go to a vendor, I want to tell them exactly what I want. I need to understand their design problem so I can efficiently post the problem to them and work through it together. Not with vapor chambers. There's black magic in there. I tell them where the heat input, the power input will be and what kind of performance I need. And this has been done for a long time by people like Celsia and Thermocore and AVC. And I'm happy to put it into their hands and then test it after they give it back.
And what about the measurement techniques? So are there more development required in terms of new innovative measurement techniques, or the current measurement techniques are sufficient?
I'm currently trying to push the envelope in how well we measure them. Let's talk for a few minutes afterwards.
Hi, Robin Bornoff from Mentor, a Siemens business. There was talk then of reduced order models. And Annie, going back to your point about the need to be able to determine unmeasurable temperature points, yeah? A model of the phone that is part of the thermal management system that could be used in operation is a great opportunity to take known properties, such as known temperatures and known powers, and then from that model provide sort of virtual sensor outputs, yeah, to the model to predict the temperatures you're actually interested in controlling. To do that, the phone is going to have to know a little more about its environmental context, yeah, to be able to do that type of prediction. Okay, so is it vertical or horizontal? I'm sure there's gyroscopes in there that could work that out. But is it being held? Yeah, is it sitting on a duvet or your covers? That information is going to have to be known to enable the value of these real-time simulation models to be considered in the future. Will a phone ever be able to know its environmental context to that extent?
Andy?
I won't say no.
It does know its orientation.
Yeah, and there's every reason. Like I was kind of kidding, because if I say no, then certainly it will happen. But especially on tape, if I'm recorded saying that, maybe that's how we can make it happen. It has a camera, and it has a human that could input conditions if that got to that point. Were you referring, though, to the phone actually kind of real-time having a model of itself?
Yeah, so sort of the emerging modeling technologies are going to get to the level where you could consider a reduced order model that could become part of the thermal management system to give real-time virtual sensor output. But such a model is going to require H's on the side of the phone. Where to get the H's from?
And like even ambient temperature is really, really difficult to get that from the phone because it's all hot. So it just starts. It depends on things like you could use an infrared temperature sensor that would somehow see outside. So if those become low cost and small enough, then we could use that. But right now they're not. We've looked at things like that for other reasons.
I think a general model to do that is achievable. As also that gentleman mentioned, the customers has different cases, so that makes the whole model very complicated. So that's a trade between the overhead of the model and the accuracy of it.
Yeah, so that's been published. If you go and search patent publications, you'll find that there's a method of determining the temperature, the ambient temperature around a sealed computing device. The potential goal being, if you're in a hot environment, and if you're in a 35-degree, very, very hot environment, you might be more willing to let your phone get a little bit hotter just so it can still do something. As far as these other situations, in doing this kind of work, you always need to accept some level of risk. And the level of risk you're asking for is, now a person picks it up from the table or duvet and places it in their hand. Is it all right for it to be hot then? Yeah, so now, and let me ask a follow-on that's in the same vein. How do you folks do it? You know, just trying to push the edge of the envelope a little bit. We're talking about touch temperature, but all temperature is local. How small might a hot spot need to be before you say, we're going to ignore that. It's only so and so big. Or how transient, how short-lived might that transient, be before you say, we're going to nip and tuck that, it's going to be okay. Anyone? No one wants to? Okay, Andy, you adjusted your glasses again. You're the man.
I need to clean them, I guess. We work with our compliance people for that. It's not really the thermal engineer by themselves. So when it gets to that point, then, like Gabriel said, it's the larger team that starts adding in there.
Do people
But I
guide
think
with customers?
there's also always exceptions, right? When you're trying to ship a product, you always have this idiosyncrasies that he's talking about. I think that in the 90s, the Japanese were famous for these idiosyncrasies in cosmetics, and they started this trend, which today Apple perfected to no end. Like, there is always defects, but I can quantify it. I can accept only that much in that surface.
Mm-hmm.
It can occur so many times, and so on and so forth. So I think your question is, are we going to be able to do like a standard thing the same way, right?
Mm-hmm.
Can we really quantify or make it acceptable to people? And I think it's personal to every manufacturer how much of a threshold they can give, right? Allow themselves to give. Am I correct?
Yes, and I think it's going to vary between all situations. So I was wondering how different people
I
approached
believe
it.
that the more you have fame and want, the more you are, you'll be allowed to have that more, right? Like I think somebody who has an Apple phone would be more. I think Jie talked about, you allowing your device to get hot because you like it, so you allow it to get hot. It's working for you. It's doing a lot for you, so you're understanding about it.
Mm-hmm.
It's okay. So it's very subjective, extremely subjective.
Okay, last question.
Hi, I'm Shreyas from Akamai Technologies. To add to your point,
hold the microphone up, please.
Sorry, are there user-defined surface temperatures acceptable because they like more performance? They can accept hotter temperatures. So, is any of you guys working in terms of enabling users to, increase the performance to accept higher temperatures?
That's an excellent question.
Yeah. We have that on the latest Surface. Surface 4 and 5 have this, and Surface Book and Surface Laptop. If you left-click on the battery icon, there's a slider bar. And there's best performance, best battery. And it trades off quite a few things. And you can choose. You can deal with kind of noisy and warm, but great CPU performance and low battery life, or cool, quiet, very long battery life in just one simple slider. So that's...
So in mobile applications as well, I mean, that's in
the tablet.
Tablets, yes.
Right.
Yeah.
Yep, mobile phones as well, yeah. They
Yes.
have options to choose between the performance and the thermal user experience. Yeah.
Thank you.
Is that feature available as a general feature of Windows, or is it only on Microsoft products?
That's a good question.
Okay, well, we'll all go and check that.
I don't think I've seen it
I haven't
on
either.
just general products, but I do see it on the Surface products.
Right.
Yeah.
I think I saw it on Windows 10.
It's Windows 10. It may. I would hope that that's.
Okay.
that
So that's
you
going
can tie
to
into
require
that.
closer cooperation between Microsoft and the individual hardware vendors.
So
Okay.
they know
Are there any
the
other
option.
burning questions that someone has to get one more in before the end? All right. That's brought us right to 5 o'clock. I want to thank everyone very much for staying late and coming to the very end of the conference. I think this was quite successful, and I'd like us all to thank our panelists one more time.